All right, so here's what you need to understand about systems of three equations. In this case, most of the time what's going to happen is you're going to now have three variables instead of two. And typically speaking, it's going to be x, y, and z, yes?
Are we just not doing 2.3?
Correct. So, in order to solve for two variables, we had to have at least two equations. When we have to solve for three variables, you have to have at least three equations. And in terms of a visual representation, how this sort of makes sense is if, normally we have the two-dimensional xy plane, and we're solving two equations. You have x and y. With three variables, we have three dimensions. And so what you would have is your normal xy plane, and then you have the z plane kind of coming at you. So if you wanted to think of something two-dimensional like the wall as two-dimensional, you have your x and your y, z is kind of coming at you. Okay, so you have this, this is the world we live in. We live in a three-dimensional world. And if one of the ways you want to think about it is like looking at the corner of a room, right? So you've got your x and y, and then your z kind of coming at you. We're not going to be doing any graphing, okay? Don't worry about that. But I wanted just to give you an idea what it sort of looks like and what you can imagine. That a point x, comma, y, comma, z can be a point in space, okay? And so that's how it kind of applies. If at some point down the road you were in a more sophisticated math course, you may have to graph something. And trying to graph 3 dimensions in 2 dimensions is kind of tricky, okay? Yeah.
Can you airdrop this?
You don't need it.
Oh.
Yeah, you don't need this. I just wanted to show you this, so you have an idea how we can have a third dimension and a third variable, okay? So 5 and 7. So here's where it would be if you wanted to know. Okay, -1, -5, and 7 is in the front. So I'm going to have this point kind of floating in space over here somewhere. All right. So another way to think about it is if, again, let's use the wall for an example. Okay. Okay. So if this is x and y, so I would go left 1, down 5, and then out 7. So there'd be this point kind of floating out here like
We
that.
won't have to.
No, you're not going to have to do that. But just understand that that's the concept. You're not going to have to graph that, but that's how it relates to an actual point. If we were thinking about 3 dimensions, that's what it would be. Okay?
Are all of the numbers...
General idea. Okay? You're going to take this system of 3 equations, and you're going to use elimination most of the time. If any of you want to default to substitution, you can, but for this, it's really not helpful. Using elimination over and over again. Okay? You're going to take 2 of the 3 equations, and you're going to eliminate 1 variable. Okay, so you're going to take it down from 2 equations with 3 variables to 2 equations with 2 variables. And you're going to do that twice. So you're going to take 2 of the equations and eliminate 1 of the variables, and then you're going to take 2 different equations and eliminate the same variable. Because what our goal here is to go from 3 equations and 3 unknowns to get it down to 2 equations and 2 unknowns. And so I maybe mentioned this the other day after your quiz, is that I'm not going to test you anymore on just solving systems of 2 equations. Because when you solve a system of 3 equations, the only way you can do that is to solve a system of 2 equations a couple times inside of that. So you can't solve a system of 3 equations without solving a system of 2 equations. So the next part, after you do that, you're going to have this new system. You're going to take a system of 3, get it down to a system of 2, and then you're going to solve that, just like we did before. And then from there, you're going to take the 2 variables. So you're going to solve this new system that you'd gotten down to a system of 2 equations and 2 unknowns, and you're going to solve for 2 variables. And then what you're going to do is take those 2 variables that you found and plug them back into one of the original equations that has 3 variables in it, and you're going to solve for that missing third variable. And that's pretty much it. So again, key concept. The key concept is I start with 3 variables, 3 equations. I have to get it down to something a little more manageable. And for us, that's 2 equations with 2 variables. So that's what our goal is, to get it down to 2 variables and 2 equations and solve for those 2 variables just like we did in 3-1. And then once we have those 2 variables, we're going to take them and plug them back into one of the originals and then solve for the last variable. Okay? So I'm going to go through one example with you. And I think after talking through the concept, taking these sort of steps down, it's really not going to be too bad. All right? The thing about systems of 3 equations that you have to understand is you must be patient. And you want to keep track of what you're doing, because if you're not organized, you can get lost in the middle of the problem. And the other thing about systems of 3 equations is that if you're in a situation where maybe you messed up one calculation or one sign, that can throw the whole thing off and has this tremendous domino effect. Which is why I'm never going to assign you too many problems. And when we get to the test on chapter 3, you're going to have to solve one of these. Because some of you will make a sign error or will make a calculation mistake, and then all of a sudden you're stuck, you sort of travel down this black hole trying to find out where you went wrong. Okay? So you want to take your time with this. You want to be really careful with your calculations. All right, so here's the problem that we're going to do. I'll make it bigger for you for now, and then I'll put it back. So this is the system. 3x minus 2y plus 4z equals 35. That's the first equation. Second equation, negative 4x plus y minus 5z equals negative 36. And the third equation, 5x minus 3y plus 3z equals 31. Again, what's really important is, in order to solve any system of equations, you must have at least as many equations as you do variables. If I only had 2 equations with 3 variables, you couldn't solve them. Okay? You have to have a minimum number of equations as you do have variables. So here's the goal. What you're trying to do is pair up 2 equations and eliminate 1 variable. And typically it doesn't matter which one you do. All right? But I'm going to show you in this particular problem why it's going to be easier in one case than another. And you're going to want to do that twice. So for example, and you can number your equations. Sometimes that helps you keep things straight. So for example, if you wanted to call this one 1, 2, and 3. You don't have to do that. That's just a strategy if you want to do that. And you could pair 1 and 2 together, and then you can pair 1 and 3 together. Or you could pair 1 and 2 and 2 and 3. Right? It doesn't matter. But the goal here is that you have to make a decision from the outset which variable you want to get canceled out so I can get it down to 2 equations. Okay? And in this particular problem, the best place to focus, I think, see, because if I'm looking at x's, we've got multiples of 3, 4, and 5 that we'd have to mess with. When I'm looking over here with z's, same thing. The thing that's sort of nice in this particular problem is that I have one variable that's sort of by itself. And so if I wanted to get 1 and 2 to cancel, if this was a 2, right, then the y's would cancel out. And then if I put 2 and 3 together, if this was a 3, the y's would cancel out. Now it's not always there's not going to be one all the time that's sort of that obvious, right? But those are the things you kind of want to look for. So if I can combine these 2 together and cancel the y, I have an equation left with just x and z. If I do the same thing with 2 and 3 and cancel the y, I'll be left with just an equation of x and z. So then I will have created 2 new equations that have just x and z, and then you solve that system however you want. Okay, and then you go back, plug in, solve for y. So that's what we're going to do for this problem. That's the strategy. So here's what it's going to look like. Okay? Again, you're going to eliminate one variable by using two pairs of equations. So remember, a pair means two. So I'm going to have two 2's, which is why when I talked about 1 and 2 and 2 and 3, there's my two pairs. So here's the pairs I'm going to put together. And I'll show you. So I'm going to eliminate the y's. And again, for everything that I talked about, you don't have to eliminate the y's. You can eliminate the x's. You can eliminate the z's. It doesn't matter. But you have to choose one variable to eliminate right from the beginning. Now, in some of your problems today, there'll be three equations, and one of the variables is actually going to already be gone in some of the cases. So you might have three equations, and the first equation only has an x and a z, so they already eliminated the y. So it would make sense then to take the other two equations and also eliminate that y, or that x, or that z, whatever. Make your life a little easier on yourself if you can. All right, so here's what I'm going to do. Pair the first two equations together. So this is all I did was rewrite them. Okay, here's the top equation and the middle equation. And then I took the middle and the bottom, and I just separated them out like that. You can copy paste, probably save yourself a little bit of time. Okay? And so now what you need to do, and I want you to do this, okay? What is it going to take in this pair of equations to eliminate the y's? What do I have to do?
2.
Multiply the bottom by 2. Okay? So do that, and then get the y's eliminated, and let's see what you get. So this is where you should have gotten after you multiplied by 2. Okay, before I just simplify that, let's just simplify that. So now I'm going to combine them together, right? So what do I get? Negative 5x, the y's cancel, minus 6z equals negative 37. No?
Yeah.
Yep. Negative 37. Okay? So in that whole situation, my goal was to eliminate the y, to have just an x and a z, and I did that. Okay? How many had that? Raise your hand. Okay, good. So in this other equation here, again, what you have to do is whatever variable you choose to eliminate first, you got to do that again over here. You got to eliminate the same variable, because my goal is to get another equation that has just an x and a z in it. And then I'm going to put those two equations together and solve it. Okay? So what do I have to do over here to eliminate the y's? Say again? Multiply the top equation by 3. Okay? Multiply the top equation by 3. That's going to give me a situation where I've got 3 y's that'll cancel. So go ahead and finish that part up. Now, here's what's really important with these kinds of problems and why I want you to be careful and go slowly, right? If you mess up one sign somewhere, you got a plus instead of a negative, or a negative instead of a positive, or whatever. That'll screw everything else up the rest of the way. What's really important to understand, especially when you get to the test, is to not erase everything. Again, my goal is to see that you understand the process, and I can see your thinking, Ryan Springer. So you should write all your work down. Because in the case where you're, 14 steps into the problem, and you're starting to figure out there's a mistake because the numbers all of a sudden got really crappy, don't abort. Because in that situation, I can still follow your thinking. So I have to go through every single one of these problems with you when I'm grading them. And when you show me your steps, I can see your thinking. So that's why showing your work's really important. All right, now, here's our next step. since I've used two pairs of two equations, and I got them down to two equations with two variables, what I'm going to do is put these two equations together, and I'm going to solve that system. And I'm going to do that on the next slide. Okay? So here are the two equations that we got them down to, and now I'm going to solve this new system. Okay? So here's my new system. Right? Now you need to solve that. Do that. Most of the time you're going to use elimination at this point. Okay? You can use substitution sometimes. So you see what I'm saying? There's no way to solve a system of equations without being able to solve a system of two equations. So if you have a system of three, you have to be able to solve a system of two. Which is why I don't need to explicitly test you on that anymore, because it's already built into these. At this point, you can solve for x or z first, but then you're going to solve for the other one too. You're going to just finish that thing up. And then I'll show you how to find y. If you think you know how to figure out how to find y after you found x and z, go for it. It's all cyclical, right? Once you find one, you plug it back in, you find another. Once you find those two, you plug it back in, you find the other one. So same kind of idea. The numbers turn out nice. So if your numbers aren't nice, you made a mistake somewhere. Okay, be careful. So that's what I'm saying. Watch your signs very carefully. Watch your calculations very carefully. The numbers should turn out nice. So let's take a look. Okay, again, the numbers should turn out nice. You have to be very careful with your signs and your calculations. And there's so many different equations at this point, right? We went from 3 equations, then we separated into 4 equations, then we got down to 2 more equations. So at this point, we have about 9 equations. And so that's where the numbering, sometimes highlighting in color helps, but you got to figure out a way to keep yourself organized and figure out where you started, where you went, and what you're trying to accomplish. That's why I spent a lot of time talking about the strategy and the concept, because you have to have that sort of theory figured out in your head so that when you start traveling down this path, you have an idea where you're trying to go. All right, so in this case, probably I could get rid of the x's, I get rid of the z's, doesn't matter. Okay? Either way, x should be equal to -1 and z should be equal to 7. Okay? Now, obviously I didn't show you the steps here because you guys know how to solve a system of 2 equations. How many got x and z correct? Okay, good. Now, if you're having difficulty in here because you made a mistake and you're getting weird numbers, you just got to go back and look at it closely and make sure your signs are right, make sure your calculations are right, make sure you multiplied by the right things, make sure you copied your problem down right. Okay, all of those things are really, really important, because if you're not getting nice numbers in this particular problem, that's where you could run into an issue. Now, the key thing here is, once I have x and z, you go back to one of the original 3 equations that has an x, y, and a z in it. I'm going to plug x and z in, and I'm going to solve for y. I might as well use that middle equation again, where the y is already sort of quote-unquote by itself. And so I'm going to plug in here. Okay, so this is just generally speaking. Now you got to take x and z and plug it in to solve for y, and use that middle equation. The middle equation where the y is kind of by itself. So I plug the -1 in for x. I plug the 7 in for z, and now I'm going to just have to get this y by itself. So I'm going to simplify here. This gives me +4. This gives me -35. Okay, so I've got 4 plus y minus 35. That's -31. Okay, y is going to equal -5. Okay, how many got that? Okay, now, last step. Just like any system, my solution is a point. And that goes back to why I showed you that 3-dimensional grid to begin with. So when you write your point, it's going to have 3 coordinates, an x, a y, and a z. Okay, and so the way I write is like this. -1, always follow alphabetical order. -1 is x, y is -5, z is 7. So if I wanted to think about it, and I'll go back to it. I don't think there's any more. Let's go back to it. -1,